Okay, good morning. Today I would like to share a paper about multi-engine reinforcement learning, which is also my research interest. The paper is promoting coordination through policy regularization in multi-engine reinforcement learning. It is a paper, the idea of this paper makes a lot of sense in my view, but I think the implementation of this paper is very complicated. The author introduced a lot of loss function that I think is very hard to tune, and the architecture to manipulate is a little bit trickier. So now let's dive into this paper. And the presentation will include three parts. The first is the motivation, and then we dive into the method. Finally, we have a look on their empirical study. It should be pointed out that they have done much experiments, and I think it's a really complicated work. So let's first come to the reinforcement learning. In reinforcement learning, an engine tries to learn to get largest cumulative reward during the interaction with the environment. And an efficient engine-wise policy exploration is appealing to train independent engine. So it's very critical for an efficient project to develop efficient policy exploration. And if the policy space is small, then you can find a global optimal policy easily and quickly. But where there are many engines to explore successful collective projects is less tractable due to the large joint action space. Even worse, it can introduce some chaos, and in this case, the efficiency for the multi-engine system can be very low. So this paper argued that coordinating the engine's policy can guide the exploration, and the exploration can help to improve the policy learning. Why does this paper validate this motivation by a very interesting and straightforward example? As you can see, there's it's just like a car, and the wheel is the engine. And if action equals to 0, the engine moves right, and if the action equals to 1, the engine moves left. So if you want to control these engines to move to the goal, both the two engines should move right. In other words, they both should select action 0. So, and this is the Markov state transition of this environment. So only both engines need to perform the same action at the same time to allow the car to transfer to different state. And this is a very straightforward example. So there is a joint action space for this system, and each engine can choose their action freely in this case. But if you impose joint action space, if you impose some structure on a joint action, in other words, you map the joint action space to a map space, then the joint action can be moderate, or in other words, coordinate, because the engine 2's action is conditional on engine 1. In this case, the author argued that there will be a enforced coordination structure on the engines, and if they introduce this structure, the trade can be much better, and the learning is much more efficient on the task with such constraint enforcing coordination, just like these three figures shows. And the solid line indicates that the training with the constraint enforcing coordination. So the motivation is validated. But how to coordinate the engine's policy can guide their exploration. That's the major problem that this paper want to solve. The first is that the engines can predict or know their teammates' policies. In this way, each engine can select action based on others, and this is called team regularization in this paper. In this way, that each engine can coordinate with each other by knowing each other's policies. The other solution is called coach regularization, where there is an extra center, or in other words, a coach, to modulate engine's policy, and so each engine can be governed by a center, be directed by a center to implement the coordination. Now let's first come to the team regularization. In team regularization, is actually very similar to the idea in multi-engine deterministic policy gradient. That's to say that MADDPG. This is the we can first see this look into the structure of the MADDPG. In MADDPG, it uses a decentralized actor with a centralized critic approach. Specifically, they train a centralized critics to approximate the value function of the aggregated observation actions pairs. That's to say, the critic is fed into the state action pairs of all engines. There's a global information, so they have global information to evaluate each engine's policy, and then we can train actors restricted to the observation of a single engine. So the actor is trained with local information, while the critic is trained with global information, but the critic can use the global information to guide the policy exploration for each engine. So in this way, the engine can avoid it's not necessary to know the global information during execution. But the author argues that these approaches depend on the engines likely stumbling on these collective actions in order to grasp their planned benefit. I think in my view, they suggest that this MADDPG did not try to guide the exploration, the joint action exploration. So they only depend on the likely stumbling. So maybe the good joint action policy happens suddenly instead of being directed, instead of to guide their engines to stump into the optimal joint policy space. So they suggest the team regularization to promote engines predictability. The engine's predictability means the engines can predict the process of other engines, while it itself also can be predicted by other engines. That in this case, the teammates get to know each other. So they introduce this loss function, which is used to train the engine to better estimate its teammates' policy. And this is very similar to MADDPG, because in MADDPG there's they also train the engine to estimate the process of other engines. But to take a step further, they use a symmetric part, because they suggest that for each engine they should not only estimate teammates' policies well, but also can be estimated by teammate well, which means that the prediction can be it is the predictability of this engine. So in this method, the traditional parser gradient loss function can be extended with two regularization paths, which is used to promote the engine's predictability. And in continuous space, they can use mean square error to do the regularization. And we can look into the structure of the team regularization when introduce team regularization into the MATDPG. And there's the parser loss to trade actor consists of three parts. The first part is the approximate long-term reward, which is the same as the traditional actor critic framework, which is provided by the critic. And the regularization part is used to promote engine's predictability, and it is showing here. And I think the tricky part of this method is that each engine's parser is equipped with additional hacks that are trained to predict other engines' actions. That's to say, for each engine, they receive local information and then they use a part of the actor to predict the action of other engines. Actually, their code is not open yet, so I'm very confused about this part of implementation. But because I think it's a little bit tricky and to manipulate the hidden layer of the actor, and I think what's more, it seems that they only use the local observation to predict the action from other engine. I think it makes less sense. So I don't know what's your opinion on this part. And another method is called coach regularization. So the significant feature of this method is the coach. The coach is the one who can observe global information and teach each engine how to perform for better coordination, but by output the global parser mask. The key is the parser mask, which is used to enforce coordination. It's a very hard technique. Okay, and this engine is also need to train, and we should train the engine to yield high returns when used by engines that he should train with the global reward of the system, because the optimal goal of the multi-engine reinforcement is to obtain a long-term cumulative global reward. So this is one of the goal of the coach. And then it should also be predictable by the engines, because the coordination you suggest should be easier to comprehend or to reproduce by the engine, or otherwise the parser mask or the coordination you suggest is not utilized by the engines. That will make no sense. So with this in mind, the loss function also consists of two parts. The first part is used to promote the predictability of the coordination from the coach, and second part is the global system as the global cumulative reward. And let's come to the really interesting part. Actually, it's called a policy mask. Each actor will learn a policy mask acting in the hidden layer of the actor neural network. So you can see that it's also a work on hidden layer. I think one of the most significant or attractive part in this paper is that they introduce many words on the hidden layer of the network. And in hidden layer, they use a softmax function to suggest the policy mask. So we can look a very simple example here. This is let's say this is the hidden layer of the L1 of the actor, and it has 9 hidden union, and the parsing mask indicates that there's the subpolitics of the system. If the subpolitic means that each engines will select the same kind of policy. And let's see this example. In this example, if there is 3 subpolicy, that means that the hidden union can be divided into multiple parts where each part consists of 3 neurons. And then the subpolicy K1 means that we can mask the other 2 neurons in each part and activate only one new neuron here. And for subpolicy K equals 2, and it will mask it will activate the second neuron in the hidden neuron layer, and the same as the subpolicy K equals to 3. So it is so the parsing mask functions as like the activation. Actually it is like let me have a think. And actually if there's the this is the one type of policy selected by this engine, and if these 2 engines select both select activate this mask, which only activate the 3rd neuron in each part, that means that they select the same subpolicy, which for backlight coordination, the mask should be equal to the mask promoted by the coach. So if they all equal to the mask proposed by the coach, their mask will be equal to each other. So actually there is a latent coordination occurring here. I think this a little bit I give a bad explanation here, so welcome for the question. And for the H actor, the loss function can be divided into 3 parts. The first part is the policy loss based on engine's own parsing mask, and it is like a traditional parsing gradient loss function, but in this case there's a parsing mask structure. And the second is to evaluate distance between the self mask and the coach mask, because the actor should predict the mask which is as close to the coach as close to the coach as possible. In this case, the coordination will make sense. And the third part is the policy logs based on the coach policy mask, which indicates that when you actually selects the coach policy mask, what's the policy lost for this actor. So it concludes 3 parts in this, and there's also some hyperparameter details. And I think it is some I think it's a little bit tricky, and how to turn the hyperparameter is another heavy work. So let's compare these 2 regularization methods. For team regularization and coach regularization, The similarity is that they both promote engine predictability. In other words, they both encourage engine to predict others' policies and itself to be easier to be predicted. And they both manipulate the hidden layer of the actor. And I am confused whether it is stable in substrate training procedure. And the difference between these two methods is that only local information is used to promote coordination during training or execution for the team regularization, but for coach regularization, the global information is here to use to train the coordination, and the local information is used during execution. I think the coach does more by introducing some synchronicity, because each engine will be enforced to produce the same parsing mask, which will in turn restrict his own action output. Now let's come to the experiments. These papers implement tremendous experiments, and I only pick some of the interesting or significant part to introduce. The first is the baseline. Actually, this paper is to encrypt MATDPG with additional regularization terms. So their comparison among baselines is actually centered around the MATDPG. And the environment consists of there are 4 environments. The first is the spec, where the engines must spec out and cover a set of landmarks. The second is the bounce. 2 engines are linked together to bounce the ball towards a target. Is actually a cooperation task. And this is the compromise. 2 linked engines must compete or cooperate to reach their own assigned landmark. It's actually a compete task. And the third is called chase, where 2 engines chase a prey that moves, and it's actually like a repulsion force from predators and wolves. And let's come to see the overall performance. And the overall performance actually indicates that the MATDPG is MATDPG plus the regularization term actually will work better in major tasks, but there is some outliers. For example, using predictability-based term regularization in a competitive task can be harmful. This makes sense because if engine can know the action from their enemies, they will have a significant response. They will have a special response to avoid the outcome. So the return will therefore be affected. And we further explore the MATDPG plus team regularization. We can see that the high performance difference between engines happens with this regularization, which means that using a predictability based team regularization is harmful in competitive tasks, because each engines will response to avoid the benefit from their enemies, avoid the benefits being obtained by their enemies. And we can validate the function of the team regularization by predicting teammates' behavior. In this case, we can see the team regularization loss function. For MATDPG, the loss function, the loss is significantly larger than the MATD-PG with team regularization. Oh, I forgot to mention, the MATD-PG plus engine modeling means that this which is similar to team regularization but not encourage engine predictability, which means that the engine is not which means that the last part of the team regularization loss function is ignored. I think this is really similar to the MATD-PG. What's your idea? Because MATD-PG also suggests the engines can predict well other engines' actions while do not encourage the engines to be predicted well by other engines. So I think this is very similar. So I have some confusion about this. And they also explore MATD-PG plus code regularization. Here is the subpolicy distribution, which suggests that during the execution, how the subpolicy selected distribution, which means that how many kinds of subpolicy, and what's the frequency of the subpolicy is selected. And from this distribution, we can say that the engines tend to switch the subpolicy because for example, for this engine, they select the portion of the subpolicy varies. It's just kind of even, which means that they tend to select each kind of subpolicy here. What's more, they also introduce some very interesting experiments to validate that the engine tend to switch subpolicy. For example, you can see this is a mask distribution entropy compared to that of a categorical uniform distribution. Specifically, if you see this is the result from the spec environment. The entropy of mask distribution is close to the categorical uniform distribution of size 3, which means that in this experiment, the engines tend to use 3 subpolicies to during the coordination and action interaction with the environment. And another interesting experiment is that the author suggests that the engine tend to select the same mask for synchronicity, and this validation makes a lot of sense because from this experiment we can say that the coordination is happens because if each engine select the same mask, which means that they suggest the synchronicity here. So that's all. Thank you. I think I have not give a clear explanation, and I'm looking for the problems and discussions. Thank you.